Welcome to the deep dive.
Great to be here.
Today we're jumping into something really cool, robots. Specifically, these super clever robots that can do amazing stuff with fewer controls than you'd expect. Our mission really is to break this down like we're explaining it to a 10-year-old, Get those aha moments.
Yeah, without getting bogged down in super technical jargon.
Exactly. And we're drawing from some lecture material actually from MIT on underactuated robotics.
That's right. It's a fascinating area. People often think robots need tons of motors, one for every single possible move.
Right. Total control.
But what we're looking at today suggests maybe the smartest robots, the most efficient ones, actually use their natural movement, their dynamics in a clever way.
Okay, so the lecture kicks off with Asimo. Remember Asimo?
Oh yeah, Honda's robot. Kind of the poster child for advanced robotics for a long time.
Totally. But if you watch it walk, it looks, well, a little robotic. Stiff, maybe.
That's a good word for it, stiff.
Yeah.
It always kept one foot flat on the ground, knees bent. Very deliberate.
Conservative, the lecture called it.
Yeah, conservative. It needed to know exactly what the ground was like, every little bump, especially for stairs. It couldn't just, wing it.
And that takes a ton of energy, apparently. Way more than a person uses. Walking.
Something like 20 times more, yeah. Which means batteries drain fast, and it wasn't very fast either. Maybe 6 kilometers an hour?
Slower than us just walking. And yeah, if the ground wasn't perfect, it struggled. So I guess the first big idea is maybe trying to control everything isn't always the best way.
Exactly. It can make things inefficient, unnatural. Asimo was like trying to over-control things, fighting its own dynamics instead of working with them.
Okay, so then they contrast Asimo with this passive dynamic walker.
Right, from Cornell. This thing is amazing. It's barely even a robot in the traditional sense, just like sticks and hinges.
Almost like a toy.
Kind of, but
Yeah.
you put it on a slight slope, give it a tiny nudge.
And it walks all by itself.
Yeah, it walks right down the ramp, just using gravity. And the way it moves, it looks really natural. Surprisingly human-like, actually.
Wow. And energy use.
Practically zero. Just gravity doing the work. So this is a huge clue, right?
That efficient walking might be less about brute force control and more about using the natural swing, the physics.
Precisely. Leveraging the dynamics, not fighting them. Nature's figured this out, obviously.
It makes me think of an airplane landing versus a bird. The plane comes in super controlled, steady.
Yeah, a very defined flight envelope, high gain control, like the lecture mentioned with the F-14 example. Very safe, very conservative.
But then you see a little bird, like a cardinal or something, landing on a tiny branch. It kind of flares its wings, almost looks like it's stopping midair.
Totally. It uses really high angles of attack. Aerodynamically, that's complex. Normally, air flows smoothly over the wing.
All right, low angle attack.
But at high angles, the flow separates, creates vortices, swirls of air. It's technically stalling, which planes avoid.
But the bird uses it to
Good.
brake, right, to maneuver.
Exactly. It uses that complex, unsteady airflow to achieve incredible agility for landing.
And the researchers, they're building planes that try to do that.
Yeah, the presenters group, they showed a video of their model plane trying to perch land. You could see the smoke visualization, the air doing crazy things over the wings.
Wild. So the point is, our current robots are often like that careful airplane, very conservative.
Dynamically very, very conservative, yeah.
Yeah.
Operating way below their potential performance because we're trying to keep everything simple and fully controlled.
And this is where underactuated robotics comes in.
Bingo. It's the science, and maybe the art, of building machines that cleverly use their dynamics instead of just overpowering everything with motors and feedback loops.
Guiding the swing, like you said, not forcing it.
Exactly. And nature is full of examples. The wandering albatross.
Oh, yeah, that flies for days without flapping.
Incredible energy efficiency, comparable to a 747 apparently. It uses wind gradients over the ocean waves. Pure dynamics.
And falcons diving, bats flying through clutter.
Or even fish. The rainbow trout using the swirls, the vortices behind rocks to basically get a free ride upstream.
They showed that video of the dead fish.
Yeah. Even a dead fish gets pushed upstream by those vortices. It really drives home how much the physics of the situation can do the work for you.
So it's not just the motors, it's the whole system interacting with the world.
Totally. And while we can build flapping robot birds, ornithopters,
The mechanics exist.
right? But controlling them to do complex things like land precisely or harvest energy from the wind like an albatross, that's still really, really hard. The control is the challenge.
Okay, so let's break down underactuated itself. Like really simple terms. The lecturer used a robot arm example.
Yeah, simple two-link arm, shoulder joint, elbow joint. Let's call the angles theta 1 and theta 2.
Okay, shoulder and elbow angle.
And imagine you have motors at each joint providing torques, twists. Let's call them U1 and U2.
Motor 1 at the shoulder, motor 2 at the elbow.
So how the arm moves. Specifically, its acceleration, how quickly its angles change speed. Q double dot, they call it. Depends on where it is now. Q, the angles.
Right.
How fast it's moving. Q dot, the angular velocities. And those motor torques.
Right. Position, velocity, and the force from the motors determine acceleration. Makes sense.
And there are equations, the equations of motion, that describe this.
Yeah.
Often the acceleration part is linear in the control input, U. So you have some terms depending on position and velocity, plus another term multiplied by your motor commands equaling the acceleration.
Okay.
Now, fully actuated. This basically means you have enough control inputs, enough U's, enough motors.
Enough knobs to turn.
Exactly. Enough knobs so that you can choose any acceleration you want for the arm, at least instantaneously. Mathematically, a certain matrix involved, F2, has full rank.
Okay, so full control over acceleration, like the toy car example.
Yeah.
Steering and gas pedal, you can accelerate forward, backward, turn, basically command any change in motion.
Perfect analogy.
Yeah.
You have independent control over all the ways it can move and speed up.
So then underactuated is?
When you don't have enough knobs, you have fewer motors, fewer control inputs, U, than the number of things you're trying to move, the number of angles, Q.
Fewer knobs than directions you want to control.
Right. The rank of that F2 matrix is less than the dimension of Q. You can't just command any arbitrary acceleration anymore.
Like the bicycle. You can pedal, force forward, and steer, change direction, but you can't just make it instantly slide sideways.
Exactly. You don't have a direct sideways acceleration knob. You have to use steering and leaning and momentum to achieve sideways motion indirectly. The bike is underactuated.
And something can become underactuated, right? Like the car on ice?
Great point. Yeah. On dry pavement, you feel fully in control. Hit black ice, suddenly your steering doesn't directly control sideways motion anymore because the tires lost grip. The system became underactuated in that state.
So why does this matter for making robots like quick and agile? Asimo tried to be fully controlled and was stiff.
Right. The thinking is that maybe real agility, efficiency, and robustness come from embracing the underactuation, learning to use the natural dynamics, the swings and momentum, even when you don't have a motor for every joint.
Instead of fighting it.
Exactly. So maybe truly agile robots need to be underactuated, or at least operate in ways that leverage their underactuated nature.
Which makes sense why walking, flying, complex manipulation, they're hard problems. They are fundamentally underactuated.
That's a key insight from the lecture, yeah.
Yeah.
These unsolved problems are interesting precisely because they're underactuated.
Okay, the lecture briefly touched on how they get those equations of motion, Lagrangian mechanics. Sounds intense.
It does, but the core idea is simpler. It's a method that uses energy, kinetic energy, from movement and potential energy, like from gravity, to figure out how the robot will move.
Like knowing the roller coaster's energy at the top tells you how fast it'll go at the bottom.
Sort of, yeah. You define this thing called the Lagrangian, which is kinetic minus potential energy. Then you do some calculus with it, and out pop the equations that link position, velocity, acceleration, and forces.
We don't need the math details, just the idea.
Right. And software can simulate these equations once you have them. They often end up in a standard form called the manipulator equations.
Okay.
Think of it like EFMA, but more complex for robots. It looks like HQQ double dot plus CQ Q dot Q dot plus GQ.
Whoa, break that down.
Sure. HQ is like the mass or inertia of the robot, how hard it is to accelerate. C contains terms related to velocities, like Coriolis forces, things that pop up when stuff is rotating.
Okay.
GQ is the force due to gravity. And BQU represents the forces or torques you apply with your motors.
Ah, so that B matrix links our knobs to the actual faces on the robot.
Exactly. And for that simple two-link arm with motors at both joints, B is basically just the identity matrix. Your shoulder torque U1 directly affects the shoulder acceleration. Elbow torque U2 affects the elbow. That's why it's fully actuated.
Makes sense. And then there was that trick, feedback linearization.
Yeah, for fully actuated systems. Since you have full control, you can use your motors, U, to basically compute what forces are needed to cancel out all the complex H, C, and G terms.
Like making the robot ignore its own weird physics.
Kind of.
Yeah.
You make it behave like a much simpler system that you want it to be, like a simple pendulum or even just staying still. You linearize the dynamics using feedback control.
Okay, clever. But what if you can't do that? What if you take away a motor? Like the shoulder motor on that arm?
Ah, now we get to the heart of it. Now your control input U is just one value, the elbow torque U2, and that B matrix becomes just a column vector. It's 2 by 1 now.
So you only have one knob, but two things are moving, shoulder and elbow.
Exactly. You can't directly command any acceleration you want anymore. This specific system is called the Acrobat.
Like an acrobat on a high bar, they mostly use their hips and arms, maybe not direct shoulder power relative to the bar.
Yeah, it's analogous. They can only apply torque at the elbow or hip joint relative to the other link. And controlling it, say, swinging it up from hanging down to balancing upright.
That sounds hard with only one motor.
It's much harder than the fully actuated case. You can't just cancel the dynamics. You have to find clever sequences of control, using that one motor to pump energy in, build momentum, exploit the coupling between the joints. It's a classic underactuated control problem.
So it requires smarter control strategies.
Definitely. Things like optimal control or motion planning, which the lecture probably goes into later.
Okay, so that acrobat makes the point. And real robots. Walking robots are like this.
Inherently, yes, because you don't have a motor that directly controls the interaction force between the foot and the ground. You control leg joints, but the ground contact is a result of the dynamics.
Ah, right. The foot contact isn't directly actuated.
Exactly. A simple model called the compass gait robot, just 2 legs, and a hip motor, no ankle motors, illustrates this perfectly. It's underactuated.
And you mentioned jumping.
Yeah, think about a human jumping. Once you're airborne, that's it. You can flail your arms, tuck your legs.
But you can't change your overall path through the air.
Nope. Your center of mass follows a ballistic trajectory determined by your takeoff velocity. You're underactuated mid-flight. No internal motor can apply an external force to change that overall path.
So flying things too. Airplanes, birds.
Absolutely.
Yeah.
And even like manipulating an object before you have a firm grasp on it, it can wobble and rotate in ways you aren't directly controlling yet. All underactuated systems.
Okay, wow. So it's everywhere, really.
It really is once you start looking for it.
So quick recap then. Underactuated robotics is all about dealing with systems where you have fewer knobs, fewer direct controls, than ways the system can move or accelerate.
Right. You can't just command any motion directly.
But the cool part, the potential, is that by embracing this, by understanding and using the natural physics, the dynamics,
You might be able to build robots that are way more agile, much more energy efficient, and more robust, maybe more like animals in nature.
instead of the stiff, energy-hungry robots like early Asimo.
Exactly. It's about working with the physics, not against it.
And the lecture hinted that the rest of that course would dig into the computational tools, the algorithms needed to actually control these tricky systems. Pendulums, walkers, flyers.
Yeah, optimal control, machine learning, planning algorithms, that's where the research frontier is.
So final thought for you, our listener. Think about the movement you see around you. Your own body, animals, vehicles, even simple toys. Where else might these principles of underactuation be playing out? Where are things moving cleverly without a direct motor for every single action?
It changes how you see movement and control, doesn't it?
It really does. Awesome stuff. Thanks for exploring the deep with us.